Hello everyone, welcome to Probability and Statistics for Data Science. In this video, we're going to talk about two very important properties of the mean of a random variable. We're going to show that the mean is a linear operation, and also then what we consider independent random variables, the mean of the product is equal to the product of the means. Let's get to it. We're going to discuss two very important properties of the mean. In order to do that, let's first remind ourselves how the mean is defined. The mean of a discrete random variable is equal to the sum of all its possible values weighted by the corresponding probabilities, given by the PMF of the random variable. The mean of a continuous random variable is equal to all its possible values on the real line, weighted by the corresponding probability density. In both cases, is if this sum, in the case of the discrete random variable, and the integral, in the case of the continuous random variable, if they converge. Okay, then the mean is well defined and it's equal to that. All right, so let's start with a motivating example. We want to model the mean cost of a latte. What is in a latte? Coffee and milk. So the price per kilogram of coffee is a random variable C with mean 2.5, and the price per gallon of milk is another random variable M with mean 3.5. And we don't want to assume that C and M are independent because maybe they're affected by inflation together. I had to re-record this video because here, for some reason, in the previous try, I went crazy and started talking about inflation for like 2 minutes. I don't know why. So I'm going to control myself and let's continue. So a latte has 0.02 kilograms of coffee and 0.1 gallons of milk. Notice that I'm a Spanish person living in the US, so I'm using kilograms and mixing them with gallons. Yeah, it is what it is. At this point, I don't know anymore. So what's the mean cost of a latte? Well, we have to multiply 0.02 times the price of the coffee plus 0.1 times the price of the milk. And this gives us the price of the latte, which we represent by this random variable L, which has this squiggly line of top because it's a random variable. Okay, so how do we compute this? We apply our formula for the mean of a quantity that depends on two random variables. Actually, I didn't put this formula. I put the formula. It is very funny. I put the formula of the discrete random variable, then the continuous random variable, and I forgot to put the most relevant one to this example. So sorry about that, but you can see the derivation of this formula in the video on the mean of a random variable. Essentially, what we do is we take all the possible values of the function of the two random variables and we multiply it by the corresponding density. All right, so here we see that because this is an integral and integrals are linear, we can actually separate this into this term and this term. So the integral of the first term and the integral of the second term. Again, because integrals are linear, because they're essentially limits of sums, we can take out these constants and just integrate what is left inside. But now we see that here we have an integral with respect to m, which only concerns the joint PMF. And when we take that integral, what are we going to obtain? We're going to obtain the marginal density of C. This is exactly how we compute the marginal density of a continuous random variable from its joint PDF with another random variable. Similarly, here, if we integrate with respect to C, the joint PDF, what is this going to be equal to? It's going to be equal to the marginal PDF of M, because again, this is how we compute marginal PDFs. So we obtain this formula where we have I was getting confused here. So where we have the marginal of C integrated against C and the marginal of M integrated against M, and we're multiplying by these constants here. What is this? By definition, this is just the mean of C. What is this? This is just the mean of M. So we have shown that the mean value of this constant times C plus this constant times M is just equal to the sum of mean values weighted by those constants. In other words, this expectation operator is linear. We can split up the mean of the sum into the sum of the means. And when we scale each of the quantities, we can bring the scaling factor outside of the expectation operator, of the mean operator. Why does this work out? It works out because of these integrals. So because the integrals are linear, then the whole operation is linear. Of course, if you had a sum, if we had discrete random variables instead of continuous random variables, the sum would also be linear. This would also work out. So we see that. And by the way, in our example, the mean cost of the latte happens to be 40 cents. And then if you're in Manhattan, the latte would cost $7. So we have linearity of expectation. If we apply any constants C1 and C2 to any function of two random variables, okay, C1 and C2, and then we sum them, and we want the mean of that linear combination of the functions of the two random variables, this is going to split into those constants multiplied by the means and then summed. So the linear combination of the means. This follows from linearity of sums and integrals, just as in our example, and this is used all over the place when we manipulate means or expected values. For example, we're going to use this to derive the mean of a binomial random variable in a very simple way without even having to consider the PMF of the binomial random variable, which has the binomial coefficient that you might be a little bit afraid of. So what is a binomial random variable? A with parameters n and theta. When we defined binomial random variables, we define them to basically motivated in the following way. We had like a coin that was flipped n times, and we were seeing how many times it was equal to heads. And all those flips were all independent. And each flip had the same probability of being equal to heads, which was equal to this parameter theta. So by that definition, you can see that we can represent the binomial random variable as just a sum of the number of times that the coin flip would be equal to 1. Each of those coin flips can be represented by a Bernoulli random variable with parameter theta. So all of this to say that if we have a binomial random variable A, we can represent it as the sum of n independent Bernoulli random variables. And now, if we apply linearity of expectation, the mean of the binomial is just equal to the mean of a sum, which is equal to the sum of the means by linearity of expectation. What is the mean of a Bernoulli random variable? Well, it's really easy. You multiply 1 times theta, and then 1 minus 0 times 1 minus theta, so it's just equal to theta. So the mean of a binomial random variable is just n times theta, and this is very easy to derive through linearity of expectation. Notice that these Bernoulli random variables are not independent. This still holds because we have not used independence anywhere when we're talking about linearity of expectation. All right, so we do not, I answered the question before asking it, amazing. We do not need independence for this. Here is a binomial with parameters n equals 20 and theta equals 0.5, and we have highlighted the mean in red. All right, so we have seen that for linearity of expectation, we don't need independence, but what if we have two independent random variables and we want the mean of a product of some functions of them? Let's write this out. By definition, we have the function weighted by the joint PDF of the two random variables. But now what we see is that because of independence, this joint PDF is going to factor into a product of the marginal PDFs. This is just by the definition of independence for continuous random variables. And now this integral can be split as long as the individual, so it can be split in this way as long as this guy converges and is well defined and this guy is well defined. If those guys are well defined, what are they equal to? Well, this is just the mean of G of A, and this is just the mean of H of B. So we have that the mean of the product is equal, that's a weird looking arrow, the mean of the product is equal to the product of the means. Notice that if we had discrete random variables, these integrals would have been replaced by sums, and we would have essentially the same situation where the mean of the product of the function of the two random variables the discrete random variables would be equal to the product of their means. This, of course, only works if you have independence, because we need for the joint PDF or the joint PMF, in case of discrete random variables, to factorize into the two marginals, which only happens if we have independence. Okay, and this is the same for discrete random variables, as I just said. So now we're going to show an example where we show that independence is needed for this to hold. And this is important to remember, because there's always this temptation to just think that the mean of the product is just equal to the product of the means. So let's see in what situations this might not hold. So we're trying to estimate the expected revenue at a certain restaurant, and the mean number of customers is 50, and the mean amount spent by the customers is $40. Does this necessarily mean that the mean revenue, the mean amount of money that the restaurant makes is $2,000? No. Let's take a look at a simple example where the mean number of customers is 50 and the mean amount of dollars spent per customer is 40, but the revenue is not 2,000. This happens because there's dependencies between the money spent by each customer and the number of customers. So here we have that this simple situation where there are nights that are very busy and nights that are very calm. And busy and calm nights happen with probability 1/2. On busy nights, there are 80 customers on average who spend $60 each. On calm nights, there's 20 customers who spend $20 each. So it just so happens that when we have less customers, they also consume less. And when we have more customers, they spend more money. And this is the effect that we're going to see when we compute the mean of the money. So now, what's the mean number of customers? Well, it's 80 times 1/2 plus 20 times 1/2. So that's just equal to 50. What's the mean amount spent per customer? 60 times 1/2 plus 20 times 1/2 is just equal to 40. So we have this situation that I explained before, where the mean number of customers is 50, the mean amount spent per customer is 40. Now let's take a look at what's the mean amount of money earned by the restaurant. Well, it's equal to the customers times the amount spent per customer. On busy nights, that is equal to 80 times 60. And on calm nights, it's equal to 20 times 20. So we have 80 times 60 divided by 2 plus 20 times 20 divided by 2. And if you compute that, that's actually equal to 2,600, not equal to 2,000, because of this effect that when you have more customers, they spend more per customer, and this dependence basically boosts the mean beyond what you would expect if you had independence. So again, you have to be very careful. The mean of the product is equal to the product of the means only under independence. So what have we learned? We have learned that the mean is linear, and we have learned that the mean of the product of independent random variables is the product of their means, but only if you have independence. Thank you very much.